Nuclear reactions. At the end of this section, you should be able to compare fission and fusion. You should also be able to complete and balance nuclear equations to illustrate radioactive decay, fission, and fusion. Nuclear fission is a nuclear reaction in which a nucleus of an atom breaks apart, producing two or more smaller nuclei, that would mean two different elements, subatomic particles, and energy. This happens because protons repel each other. Remember, protons have the same charge. They're positively charged, and like particles repel each other, unlike neutral particles, which are neither attracted nor repelled by each other. In elements that have large nuclei, that is the heavier elements, they contain many protons, so there are very strong repulsive forces. As a result, this makes them unstable. And as a result of that, they split apart into atoms that have lighter nuclei, and this releases a lot of energy. So picture this. If we look at this nucleus of an atom, or a partial nucleus, we haven't shown any neutrons, but we have many positive charges close together. They are going to repel each other and break apart into smaller, lighter elements. I haven't drawn in the neutrons, but there would be neutrons in this original atom as well, and so you would have neutrons in the newly formed nuclei as well. And because there are fewer protons in each of the nuclei that form, the number of neutrons that would be there are sufficient to sort of separate the protons and keep those elements from further separating, or to keep them stable. So there are uses for nuclear energy because there is a lot of energy released. It can be used to power generators that make electricity, and you've probably seen pictures of these. We don't really have them in our neck of the woods here in Western Canada, but there are nuclear power plants just south of us in the state of Washington, and they have different designs, but this is a common design, and basically you'll see these big sort of cone-shaped stacks and a lot of what looks like smoke coming out of them. There's really just steam, because what they're doing there is they're using the nuclear power to heat water, to turn turbines to generate electricity. Nuclear energy can also be used for nuclear weapons. And this is sort of the dark side of nuclear energy. Let's compare chemical reactions to nuclear reactions. In chemical reactions, the atoms are simply rearranged, bonds are broken, and new ones form. In nuclear reactions, we actually have atoms that are changed, and we can produce whole new different elements. The part of the atom involved in chemical reactions is only the electrons. Electrons can be shared, or they can be transferred from atom to atom. In nuclear reactions, all of the atom is involved. Electrons, protons, neutrons, and even other subatomic particles that we haven't talked about. The amount of energy released is different. With chemical reactions, a small amount of energy may be released or even absorbed, but with nuclear reactions, huge amounts of energy are involved. And something different about nuclear reactions as well is that electrons can actually be formed in the nucleus, and that doesn't happen with chemical reactions. Induced nuclear reactions. Alpha, beta, and gamma decay occur naturally, but we can also induce nuclear reactions to take place, and we do this whenever we want to create the power plants to generate electricity, and also for the nuclear bombs that we talked about, or nuclear weapons we talked about earlier. The way this is done is that nuclear reactions are forced by bombarding a nucleus with alpha or beta particles. So here's an example. An alpha particle, which is simply a helium nucleus, can actually be forced to strike nitrogen, a nitrogen nucleus, and the result is that the nitrogen nucleus breaks apart slightly to form an oxygen nucleus and a hydrogen nucleus. So really all that's been achieved here is that the helium has caused the nitrogen to basically break apart into oxygen and hydrogen. Note that the alpha particle is a reactant and not a product, as in natural decay. Take a look at figure 719 in your book on page 314 to help you visualize what this looks like. So this reaction can be written in two ways. The first is the one shown above right here. And the second way is shown right here. Notice that we're using the symbol for the alpha particle, which again is simply just a helium nucleus. It strikes the nitrogen nucleus and we get an oxygen nucleus, and we get a hydrogen nucleus, which is shown here because it shows us that the atomic number is 1, and it shows us that the mass number is 1, which means that there can only be one subatomic particle there, which is a proton. And so this is another way of showing a hydrogen nucleus, just 1 over 1p. So on that note, let's take a look at some subatomic particles that you'll see in nuclear reactions. The one we just saw in the reaction above, the proton, can be written two different ways, as we've discussed. Neutrons can only be shown one way. The helium nucleus, or the alpha particle, is written in two different ways, which we've seen before, and the electron, or the beta particle, also can be written in two different ways. So most of this should be a review to you. And as you've seen in the reactions above, you've probably figured out that induced nuclear reactions, like natural radioactive decay reactions, must be balanced. Nuclear fission of uranium-235. The following fission reaction occurs in Canadian nuclear power plants and fission-style nuclear reactors. It involves colliding a neutron, which has no charge, with a uranium nucleus. Have a look at figure 720 on page 316 so you can better visualize what's going on. So in this reaction, one neutron is fired into a uranium-235 nucleus, and the result is that that neutron fuses with that nucleus to give us uranium-236, but this is highly unstable. And it doesn't stay like this for very long. It will spontaneously split into krypton-92 and barium-121, and also release 3 neutrons and a whole lot of energy. And of course that's what we want, because we want to use it in a nuclear reactor. You probably realize that this is the graphic that we looked at up above earlier on, or that was actually placed up above earlier on. You have the graphic for this reaction shown earlier in this packet. So let's just summarize. A new isotope of uranium results, but is unstable. It immediately splits into 2 smaller nuclei, releasing several helium nuclei and a lot of energy. What happens with these neutrons as they come flying off of the reaction is that they are carrying a fair amount of momentum as well, and if they strike another uranium-235 nucleus, they're going to cause the same reaction. And so what this begins to do is it sets off a chain of reactions. So the neutrons produced trigger more nuclear reactions by striking other uranium-235 nuclei. If you take a look at figure 7.21 in your textbook, which is on page 318, it actually shows a nuclear chain reaction. And you can see that if every time one of these occurs, quite a bit of energy is released, adds up to a huge amount of energy being released in total, and it can lead to very violent nuclear explosion. So if you're going to use this type of a reaction in a nuclear power plant, you wouldn't want to have a violent nuclear explosion. Obviously, you need a way to control the reactions. And so cadmium and other materials that absorb neutrons are used for cadmium rods can be used in nuclear power plants to prevent the reaction from becoming uncontrolled, which would of course result in perhaps a catastrophic meltdown, as we've seen in history. So Canadian nuclear reactors are used for nuclear technology, for power generation, and for medical uses. Here we see a power plant, and over here we see one of the uses of these nuclear isotopes that can be produced in this case. There's been some radioactive element that accumulates in the bones that's been injected so that they can then do some imaging using X-ray equipment. And so basically the idea is that wherever this material accumulates is an area of a lot of activity, and it could mean that there's a bone that's healing, maybe a broken bone, or it could mean that there's arthritis in this area, or it could also mean that there's a lot of cell activity due to cancer. The reaction that takes place in Canadian nuclear power plants is summarized below, and it should look familiar because it's the one we just looked at above. Here we have a little graphic of a CANDU reactor. That's a Canadian Deuterium Uranium reactor, and it shows a few things. The nuclear fuel produces heat, which is used to make steam, and the steam drives turbines that are connected to electrical generators. And it's called a Canadian Deuterium Uranium reactor because deuterium is an isotope of hydrogen 1 that is twice as heavy, as it has both a proton and a neutron in its nucleus, so it's not a typical hydrogen atom. So the heavy water produced by the special hydrogen nuclei that have an extra neutron in them produce heavy water. And the heavy water is used as a moderator, or it helps to actually control the reactions, in addition to the control rods that can be pulled out or pushed in to kind of control the reaction. One of the problems with this type of technology, any nuclear technology, is that it's going to produce some hazardous wastes, and this includes the heavy water, which is in close contact with the radioactive material, and also the control rods, which actually also pick up some of the radioactivity. And a major issue is how to store them or dispose of them, since it takes a long time for them to no longer be radioactive. So nuclear fusion is kind of the opposite of nuclear fission, in that we're actually taking nuclei and fusing them together and energy is given off. It occurs naturally on the sun and also in fusion reactions. And the reaction is summarized right here, where we have two hydrogen nuclei with different isotopes being fused to produce a helium nucleus, and we have one leftover neutron, and with that we have energy also being produced. So we fuse two hydrogen nuclei to produce a helium nucleus, a neutron, and quite a bit of energy. So researchers have been working for quite a long time to find a technology that will allow us to extract energy from fusion reactions. One of the difficulties is achieving the high temperatures and pressures needed to do these reactions. And another is simply finding a way to contain a reaction that's so hot that no vessel can hold it without being destroyed. So you can have a look in your textbook on page 321 to see how fission and fusion reactions compare with each other. Basically, in fission reactions, you have heavy, unstable nuclei split apart into two smaller nuclei, and in fusion reactions, you have two lightweight nuclei joined together to form a heavier nucleus. And there are quite a few other differences that you should be familiar with. So have a look on page 321 and see if you can figure out the difference between fission and fusion reactions.